Good morning and welcome to the second invited speaker, who's going to be another exciting talk. So today's speaker is Jerry Chow, who is an IBM Fellow and Chief Technology Officer for quantum-centric supercomputing at IBM. In his role, he's responsible for defining how quantum integrates as a core pillar of IBM's hybrid computing strategy, designing forward-looking roadmap where quantum systems operate seamlessly alongside GPUs and classical accelerators, delivering performance, reliability, and capability that the market can understand and trust. He's a recognized leader in the quantum computing industry, and he plays a key role in sustaining IBM's technology leadership as the field moves from scientific demonstration to commercial adoption, and they're very close. Trained as a physicist specializing in superconducting qubit quantum computing, he graduated magna cum laude with a BA in physics from NMS, in applied mathematics from Harvard University, and earned his PhD from Yale University in 2010. He joined IBM as a research staff member at the same year. In 2016, he co-led the launch of the IBM Quantum Experience, the first cloud-accessible quantum computer, helping catalyze the worldwide quantum developer community. In 2021, he was elected Fellow of the American Physical Society, Division of Quantum Information, and received the Yale Science and Engineering Association Award for Advancement of Basic and Applied Science. So today he's going to talk to us about what they do at IBM, and of course, what's the future, which is, I think, very relevant to our community. So, Jerry, thank you very much.
Thank you very much. Okay, thank you so much, Dimitris, for the very kind introduction. And good morning to you all. Thank you for being here on a Saturday morning to hear me talk. I'm very excited to be able to tell you a little bit about what we call quantum-centric supercomputing. And I know, the primary topic of this conference is certainly about computer vision, and I love to try and see where there's going to be some of these threads of alignment, right, as we move forward. And so I want your attention for the next 50 minutes to take a little bit of a leap with me, right, into the quantum realm, to hear a little bit about what we're doing across the spectrum of hardware, software, but also a big part of how we're integrating quantum into computational workflows that you're probably all very familiar with in terms of using GPUs and CPUs of today. So I'm certainly here representing IBM Research, and from IBM's research point of view, a core part of our goals is to drive breakthroughs across 4 key areas. Silicon, right, if you think about that, that's the foundations of computing in terms of how we've scaled with Moore's Law and certainly the capabilities of where we've gotten with semiconductor-based computing in the past 50+ years. But we also have a strategic direction to push on quantum, right, where quantum is really how we advance to the next realm of computing that is beyond what we can do with classical computing, and solving those challenging and intractable problems at scale on problems that we probably even already wrote off, right? Decided that we weren't going to look at using classical means. And then, of course, we continue to drive AI, but from an AI perspective, we're looking to really focus in on how we can build it natively for systems that are efficient and modular for scalability. It all ties together with algorithms, though, right? A big part of this is the algorithmic push is really think of it as the mathematical bridge towards applications. And we really drive value and enterprise scales when we are able to get all the pieces together working towards solving the hard problems that are out there. And here, there's certain key primitives that we're looking at, from Hamiltonians to partial differential equations, optimization, and stochastic processes. Now, I'll give you more of this quantum lens first, and then over the course of the talk, I hope you see how these are all tying together, right, across these different areas that we're driving at IBM Research. This is our published roadmap, which is public in terms of what we are targeting with our quantum computing efforts. It's a lot to look There's a lot to digest. I don't ask you all to look at it here. But what I want to show you here is that we have a very explicit roadmap culture at IBM, targeting really the capabilities and from a technology and innovation perspective at the bottom in what we call an innovation roadmap, driving really the technologies that are necessary to continue to scale and bring forward quantum as a usable type of computing capability. On top of it, though, we also focus on a roadmap of what we can deliver to our clients and to the world. Because it's not enough to just have the innovations and a lot of the physics and engineering. It's about how you actually make it consumable and how you bring it as part of a real computational platform that is leverageable in order to do research, scientific discovery, and certainly, over time, drive domain expertise to lead towards enterprise scale applications. And so really the upper part of the roadmap shows a year after year progression of increasing abstraction, right? How do we actually get layers of software stack more and more abstract so that it, over time becomes capable of actually delivering, for example, application libraries, right? That underneath are leveraging some combination of quantum and classical computing altogether. Now, to really kind of boil that down into some key milestones, I like to show this progression of key items. 10 years ago, we first put a 5-qubit quantum processor online. It was called the IBM Quantum Experience. It really opened up the path to a different way of experiencing or accessing quantum. Before that, you had to always either work in a quantum physics laboratory, right, or know someone who worked in a quantum physics laboratory to really do anything at a scale that you could even do, for example, publish papers. Then we progressed to 2023. 2023 is when we demonstrated what we call quantum utility. And this was scaling along that roadmap of the underlying quantum processor capabilities to a point that you could run quantum programs or quantum circuits that are beyond exact classical simulation. That's a key point. That it says that at a certain scale of what you could actively really run on a physical device, that you could run something that you cannot exactly simulate on a classical computer. So that says that there's at least something that we should be looking for in terms of a differentiating capability of quantum over classical. Then there's this target for this year, 2026, which is what we're calling quantum is real. And here it is twofold. On one side, it's what we call provable scientific quantum advantage. And what that is that for a particular task, that quantum is going to beat all potential classical methods at solving a particular problem, in either being cheaper, in either being faster, or being more accurate. It's a hard bar to hit, right? It's one where you said that you're gonna beat those exact classical methods, but you're also gonna beat all other approximate classical methods to solving a same problem as well. And there's a rigorous definition of how to achieve this that we've been defining, and that one that we're working with various scientific and academic communities to really try and make happen. But a flip side of that is this other piece, which is that quantum now is also starting to be applied to real use cases and being leveraged to simulate particular problems of interest, which I'll get into in a little bit as we discuss further. Then looking forward, there's a key mark for 2029 time period when we wanted to deliver the first fault-tolerant at-scale quantum computer. This will be one at the scale of around 200 logical fault-tolerant qubits and operating circuits of 100 million operations. And I'll describe a little bit more of what I'm talking about when I mean these quantum circuit scales of number of qubits and number of operations and what that really means. But then looking forward, I think many of you probably have heard of quantum being potentially applied for cryptographically relevant problems, right? Shor's algorithm, breaking all these encryptions. And so there we're seeing just from the progression of where we are with these machines that we'll reach that kind of milestone into 2030s, being able to run what's called Shor's algorithm. Now, from IBM's perspective, our strategy is twofold. On one hand, we need to build and deliver a platform that really scales and shows the differentiating capability of quantum over classical. That includes both making progress in terms of our hardware capabilities as well as the software platform exposure of those capabilities. But then on the other side of it, it's really about driving an ecosystem. And it's important to actually activate a network of enterprises, national laboratories, academic institutions, to all help advance algorithmic discovery to actually use these machines. Because it's an exciting time we're in, especially if we're talking about that we're at the point with some of these capabilities to run something you can't do classically. But what can you actually leverage that for? And so a lot of the drive here is actually on near-term heuristic algorithmic advantage, leading towards scalable algorithms that are going to run when we have the more fault-tolerant machines. And so really from the algorithm perspective, we look in these 4 key computational areas, right? That these are ones that we feel have the opportunity to be really disrupted by quantum in terms of how they can be solved. Hamiltonian simulation, I think this one people probably have heard about in terms of even Richard Feynman saying many years ago that nature's not classical, right? But that quantum computers have the opportunity to solve Hamiltonian simulation problems in ways which you can actually directly evolve the quantum states, right? And those same physical laws that describe the Hamiltonian are available to you in terms of how you program and leverage the quantum computer. Optimization, right? And this is maybe where there starts to be some of the connections to a lot of the work that you're all in, right? That optimization problems, of course, can be extremely challenging with the number of variables and with the number of options. And here the question is, are there ways of using quantum algorithms in terms of finding quantum amplification solutions to find optimal solutions? Machine learning, of course, right? And here machine learning, really there's the ideas of using quantum kernels to actually capture complex group symmetries and use that as, for example, kernel methods for classification and so forth. And then partial differential equations, a direction that certainly impacts many, many different industries, but ones where we know that there's nonlinear dynamics that certainly scale very difficultly to run in any kind of classical simulation space, and where we have the opportunity to use some of the complex, multidimensional, exponentially large Hilbert spaces of quantum computers to look at. Now, looking at these algorithmic areas, right, it's kind of interesting to see that the potential market capture of where this impacts the world has the potential to be at the $450 to $850 billion range. Right? So this is why people are so excited about quantum computing. This is why you hear about all these publicly traded companies that are being put out there, all the buzz that you hear about is because the promise is really a very, very large potential economic industry. And this is just based off of the things that we have some level of provable algorithmic advantages in those 4 areas. There's still to be seen all the things which we haven't yet proven or we haven't yet discovered. And there we could potentially see even larger value creation. And so the way that we see this progressing, right, is that we're building a platform to drive this algorithmic innovation. On one hand, I mentioned before that we're building the platform, and this kind of platform is actually is an evolution of when we first released our 5-qubit computer on the cloud, that it lets us today deliver at the 100-qubit processor level, quantum computers that are available to the entire world, and allow for integrations and software development that build on top of it. And from the adoption perspective, we have an open source strategy, and this is what we call Qiskit. It's an open software development kit that provides flexible and comprehensive interfaces for attaching on either functions or integrations into the software stack. And here we're really trying to drive open science tools that drive towards developing those novel algorithms. So where are we today, right? With a lot of the capabilities that we have, we're building already the most performing quantum computers at IBM. The way to think about how to compare these is really to think about a couple of key metrics. There's scale, there's quality, and there's speed. Right? From the scale perspective, there's the number of qubits that you have available to run quantum circuits. Right? So if you think about the computational primitive that is relevant for a quantum computer. It's really a quantum circuit. You can think about it as like a rectangle in terms of the number of qubits that you have in a register and the number of operations that you can actually perform across those sets of qubits in the other dimension. The larger circuit that you can run, the more complex type of problem you can solve. Limitations of today's machines in terms of why you can't just make these really, really long are errors that occur in the physical qubits themselves. And there are near-term strategies to use quantum error correction to deal with those that allow us to get to our quality of these circuits that lets you already do interesting things. But the long-term path is to use what's called fault tolerance to really allow you to extend these types of circuits to much longer numbers of operations. So scale, quality, and then another one is speed, right? The way to think about quantum computing also is that they're not single-shot type machines that you run one problem or one circuit and you've got the answer that you need and you're done. But in fact, it's actually going to be something that is integrated with your classical computing methods as a part of a larger classical plus quantum programming routine. And so there's actually workflows where you need to pass information back and forth from your classical machine to your quantum machine, back and forth in short loops, in short iteration loops, where the speed actually matters a lot. And so when you run these types of problems where you might actually need tens of thousands to hundreds of thousands of quantum circuits that all are changing, the wall clock time of how quickly you're able to get the information in and out is very important. We have a particular measure here called CLOPS, or circuit layer operation per second, that is critical for really driving these types of workloads through to get reasonable answers out of your quantum computers. There's a lot of benchmarking that happens out there. There's third-party benchmarking done by foundations like the Unitary Foundation. But really, this is an area that's picking up a lot of steam in terms of looking at how do you actually measure the comparisons of these different types of quantum computers and quantum computing modalities of building these qubits out there. And then from an ecosystem perspective, we have a business ecosystem at IBM called the IBM Quantum Network of over 325 members. And these include, I mentioned before, enterprise institutions. It includes academic research institutions and commercial partners and startups that are actually building integrations into our software stacks. Yeah, and so really, we've seen this progression from going from just 10 years ago of putting the first quantum computer on the cloud and seeing the first paper get demonstrated about a week after we launched it on the cloud. It was what's called a Mermin inequality demonstration on our 5-qubit quantum processor. To now today, where we've seen over 6,000 papers in these 10 years that have been leveraging our quantum hardware and software capabilities, right? And so this is something that, for me, has been extremely telling and rewarding, that by getting it out of the hands of just the physicists, but into the hands of the developers and those that are looking to really build and to explore, that there's a tremendous amount of discovery that can really happen. Okay, so now I want to get into this discussion more about the usability of these and the applicability of these quantum computers for useful problems. I mentioned quantum circuits before. And so the way to think about the landscape of algorithms and applications is to really see kind of the picture of how large quantum circuits need to be to really solve provable instances of some of these types of problems. Hamiltonian simulation, optimization. Every one of the dots on this plot is a paper that a theoretical group has actually written to say that these are the resource estimates that are needed to solve some kind of problem in that space. So you see both dimensions of the width, the number of qubits, and then the depth, the circuit size, the number of operations that you need in your quantum computer. And these operations, if you know a little bit about the quantum mechanical gates and things like that, these include 2-qubit entangling gates that actually let you drive entanglement between your qubits in your lattice. And so you can see that most of these are out in the several hundreds of thousands or even more of qubits, and operations of on the order of certainly out millions to hundreds of millions and billions. But we have our waypoints for getting there. Remember that large roadmap we have? our path towards fault tolerance brings us right into the range of looking at these types of problems with Starling, which is our target for 2029 at 200 logical qubits and 100 million gates, and then with BlueJ, which is the 2033 plus timeline of 2,000 logical qubits and out to 10 billion gates. But there's a question of about all the space in between too, right? And there's a lot to be done in terms of the discovery phase of what can be done in between. And so I'll touch on that in a little bit, but first I will talk to you about our roadmap towards building these kinds of fault-tolerant machines as well. And so Starling is something that we've already started laying out our blueprints for building. This is a physical rendering of what we see will be the physical space needed to build what we call IBM Quantum Starling. And from this fault-tolerant quantum error correction perspective, right, the idea here is that fault tolerance says that we're going to actually keep up with the errors as they occur, and we're going to use an error correction code that is expanded out amongst a larger number of physical qubits so that we can keep track of those errors and correct them. But there are key aspects of building this kind of fault-tolerant architecture, right, that actually take you from something that's more theoretical to something that's actually engineered in practice and that you can physically build. And so you need a criteria that's appropriate for scaled architecture. So at first, you need something which is a fault-tolerant code, where you can actually suppress logical errors enough so that you can actually proceed with meaningful algorithms. You need to have certain operations in terms of how you can actually address these fault-tolerant qubits, how you can apply logical instructions to those logical qubits. And you need to be able to perform these measurements where you actually need to read out the information from these qubits. And then from an engineering perspective, you need to build these in ways that are scalable and economic and efficient. And you need modularity so that you can actually connect these types of architectures together and replace them when you need to. And then in terms of efficiency, that you can do this without needing, say, a football field of space, but traditional maybe data centers. Data center size of space. And so we made significant progress to really removing a lot of those roadblocks to get towards fault tolerance at scale. We published a paper a few years ago which demonstrated a fault-tolerant error correction code that required 10 times less than what was the known best at the time. It meant building a machine like Starling or BlueJ at the scale of using just 10,000 or 100,000 physical qubits versus perhaps needing millions of qubits. So that type of resource reduction in terms of the physical qubits needed was a big part of actually saying that we can potentially build this. Then we needed to show that you can actually perform operations and also decode and detect the errors that are occurring on this kind of lattice at the same time, kind of in the real-time sense. And we published 2 papers last year that really showed end-to-end resource estimates and operational capabilities of this, what we call a bicycle code architecture. Now, the way to understand what this looks like is actually that it's a topological error-correcting code. It's actually a number of qubits that are laid together on a lattice. Well, what it actually is, mathematically looks like is a torus. And so it's a torus that has many connections between the various qubits, and the density of these connections is actually what brings in the error correction. Of course, we don't physically build this as a donut. We actually have to rely on semiconductor engineering. And so it's here that we actually use 300 millimeter wafer capabilities and a lot of our know-how of using advanced silicon packaging to let us build very, very advanced chip stacks to actually realize this with a superconducting qubit architecture. Now, this is really something that's relied on many, many years of engineering, of adopting, right, capabilities that are certainly very common and well known for building the chips that are in your phones or in your laptops, but getting them to work with superconducting qubits so that they can also work in cryogenic environments and yet still preserve the quality of the underlying quantum information so that you can scale these reliably. Now, we've been doing this by integrating things like through silicon vias, bump bonds, multi-level wiring. Again, techniques that are very common, but ones that are now able to be used at the scale of superconducting qubits. And so I won't go into too many of the details here, except that there's building this overall architecture in a modular way. There are various different physics demonstrations that we've been working on to show that we can actually build this type of architecture. We've realized that many of these in the laboratory to actually show that we can have think of them as the underlying ingredients towards building out the larger scaled architecture. But also, I think what we're starting to see is really the complexity of these devices. So today we have devices that are like what's shown on the left here, that are released to the public, what we call IBM Quantum Heron. And what we're building towards with these very advanced quantum error correction codes is what we have on the right, which is our Loon device. And this is a fun X-ray micrograph of a 300 millimeter wafer where you can start to see the complexity of the underlying, in the underlying silicon of the connectivity that's required. Where something like Loon and beyond and towards Starling is going to require a lot of automated design flows as well to even network and lay out these types of devices. And so it's with this that we are really pushing on using leading edge semiconductor fab to build our quantum computers. We leverage actually the Albany Nanotech Center, which is up just a little bit north of our research laboratory in New York. And then we just recently announced this joint venture, which is backed by the US Department of Commerce of Anduril, which is a pure play quantum foundry to build these types of quantum wafers, right, for the supply chain, certainly for IBM, but also for the rest of the quantum industry, right? And it's something that we see that's going to be very important, certainly for us at IBM, but also for America and for the world, to have these capabilities of delivering engineered solutions to these quantum technologies built at scale of 300 millimeters. Now, that's not the end of the story, though. From building these types of fault-tolerant machines that it's just a chip, right? So these are superconducting qubits. Superconducting qubits need to be cooled down to very low temperatures. So we used what are called dilution refrigeration technology to cool them down to around 15 millikelvin. You might have seen pictures of these fridges in the past. They look like cylinders. They have a bunch of wiring inside of them. They kind of look like golden chandeliers. But we're now building towards, for Starling and for Blue Jay, a different kind of modular cryogenic infrastructure. One that's really amenable to the data center environments. One that's also, we'll say, more energy efficient maybe than certainly a lot of the GPU types of expansions that we know that are happening. But one that really also lets us scale this in a modular way. So what you're looking at is a internal prototype for a new modular cryogenic infrastructure that we call Union. So they're actually large rectangular shells through which we actually put these cryogenic cooling engines into, and then we can kind of scale these out to a larger number to realize a footprint that we need for Starling. So what you see in the colored sort of blueprint, there's what we see as the real realization of what we need to build for Starling. It'll take something like 3,500 square foot of space, 1.5 megawatts of power. And what you see in the picture is our first Union 2-cell system that we're cooling down and testing right now in the laboratory. Now, of course, beyond that infrastructure, there's all the other components that go inside too, right? So from a supply chain perspective, there are things like, might sound boring, but things like signal cables, right? They need to work at a large density, but also work in these cryogenic environments. There are other passive components that need to sit inside the infrastructure, as well as active ones like amplifiers. There's classical control infrastructure, right? So actually building CMOS ASICs, both that sit in the cryogenic environment and outside to control the microwave and magnetic flux pulses that control these qubits. And then there's also this problem of capturing the errors and decoding the errors in real time. And that's another kind of ASIC that we're building using traditional silicon that allows us to really keep up with the error correction code And this is all sort of built into the overall, supporting infrastructure of what these fault-tolerant systems are going to look like. Now, some of the exciting directions here also that there's a lot of work in error correction today, right? So with these quantum circuits, there are ways of performing what are called dynamic circuits. So as we are performing circuits on these qubit registers, we can actually perform measurements of certain qubits, both in space and in time, and we can leverage what are called error detection space-time checks to really improve the fidelity of the types of circuits that we can run on these devices. And so this is an exciting direction that we see where actually by using a lot of this kind of dynamic circuit capability, we're going to have this path of growing our capabilities of error correction from today, where we're handling errors kind of at a sample level towards the error correction codes that are going to be leveraged for fault tolerance. And so this is actually an area there's a lot of active research working with, for example, those in the community to develop a lot of these kinds of codes that are going to leverage, in fact, classical infrastructure sitting on top of even the quantum infrastructure, for example, GPUs as part of the dynamic circuit loop to perhaps perform outer decoder types of hierarchical codes that ultimately give you a better result for your underlying circuit executions. Okay. Yeah. So, but really this is kind of the direction that we see, that integrating with classical and other types of accelerators is important to actually drive the usefulness of what we can run on the quantum computers themselves. And so we have this vision, certainly, of that you need all these pieces for your future of computing. There's CPUs, which are good at doing your basic math. Of course, GPUs, which have completely changed our world with what we can do with tensors and AI. And then for QPUs, really the core element is that we need to rely on them to run these quantum circuits at scale, because that's really the differentiating computational construct that wouldn't map well onto any of these others in terms of CPUs or GPU resources to run those circuits. And so how best can we use all three of these together? So looking back at this map, right, of where we were looking at these different kinds of simulation and application areas in terms of resource counts, there's this open question that is, what is in between us getting from machines today towards Starling and Blue Jay, which we know can start to address these other provable application and algorithm instances. We actually published this work that was with the Riken Institute in Japan, which actually let us look at a molecular simulation of iron sulfide compounds, so 4Fe4S, using a quantum-centric workflow. So we actually use a quantum computer paired with a high-performance, in this case it was an ASIC-based computer that Fugaku, right, which is the most performant, the largest supercomputer in Japan. And we were able to perform a diagonalization to get the ground state energy of this molecule using 77 qubits and running out to 10,000 or so gates. And what's interesting about this is that we were able to define a workflow using an algorithm called sample-based quantum diagonalization, where the quantum and the classical computers are working hand in hand, but on the same problem together. To solve these types of molecular simulation problems, they're often too large to actually fit onto a full classical computer to diagonalize. There's just too many interactions, right, between the underlying electrons. And so the best classical methods find ways of getting the right subspaces to then try and diagonalize. But even getting the right types of subspaces is itself very challenging, and it's not always clear where to start or where to iterate on. And so what we're doing here is actually using the quantum computer for that first step. We're going to actually sample configurations on our quantum computer that maps onto the molecule of interest. And by doing that, we use the quantum computer to find these subspaces. We get those results, and we perform the diagonalization still on the classical supercomputer. And we do this iteratively until we get lower and lower energies. So this is a closed loop type of workflow where we can actually start to use a large amount of classical compute resources in the same workflow as the quantum computing resources. Now, the results that we got for this are already starting to be competitive with some of the best classical-only approximate methods. We're not yet beating there's a state-of-the-art technique that's called DMRG. We're not beating that one yet. But now you can start to see that we're in the same ball game. Right? That you can start to almost ask, well, how much supercompute time can I offset by using this quantum plus supercompute workflow? Right? And so now this gives us an avenue to look at kind of that advantage thread I mentioned before of cheaper, faster, more accurate along these types of dimensions. At some point, as we scale the hardware, we'll get to a point where perhaps we'll be able to beat that accuracy of the best known classical-only methods. Using a very similar technique, so that one was for ground state energies, we're also able to do a similar kind of technique to actually look at the electronic structure of a lab-made molecule. So we partnered with experts in scanning tunneling microscopy. So they use an STM tip to actually build what's called a half Mobius molecule. Okay, so I think people know about the idea of a Mobius strip. Mobius strip, you kind of go around twice on a Mobius strip to get to the same place. This is a half Mobius molecule where your electron phase takes not 2, but 4 loops to go around to return to the same place. So we were able to actually build this molecule in a physical lab, which we, at least on theory, predicted should have this half Mobius electron configuration. And then we were able to use a quantum algorithm paired with HPC to simulate that electron structure and validate that it in fact did have this kind of half Mobius topology. Now, again, this wasn't something that could be not done just purely with classical simulation. But in this case, working with some of the researchers, it was actually easier for them to just set up this kind of simulation using the quantum plus HPC workflow than finding the right kind of breakdown of how to map it onto a classical proximate method. But you're also starting to see it enter the loop of these physical experiments that are verifiable, right? And in a lab, actually built molecules that are being also simulated using a quantum computing workflow. Also working with the Cleveland Clinic, they're looking at using the same type of technique to understand some of the molecular structures that are required in skin cancer phototherapy, right? And so this is actually a project that recently was awarded $2 million by our partners at Algorithmic and Cleveland Clinic to look at these potentials for photoactivation pathways. So you're starting to see also the biological relevance of some of these quantum plus classical simulation capabilities. And then there's also the question of, well, what else can we do with high-performance computing capabilities and GPUs? So it turns out, right, so even that problem that we worked on with Riken, where they were using Fugaku, that we could do better, and we could reduce the amount of time it took to perform the classical diagonalization step. So this was in a collaboration with AMD and Oak Ridge, where we took that same type of problem, this molecular simulation problem, but did the diagonalization step using GPUs, right? And by using OpenMP offload, we were able to see over 100x performance boost in doing that classical only step. And so really now the question is, how best can we really take these large-scale problems that we know are pushing the boundaries of what we use supercomputers for, and break them down so that they use QPUs or CPUs or GPUs in the best way. And these are starting to show those types of examples. Now, it's always fun to quote this line by Richard Feynman, that really the the fundamental test of all knowledge is experiment, and to push the boundaries of where we can really experiment. And so this is what I'm extremely proud of, which is that we actually worked with Cleveland Clinic and again with the collaborators at RIKEN to push the scale of chemistry applications. So we talked about some of those molecular simulations earlier, but working with this one professor at Cleveland Clinic, he really wanted to see how large could we go. And it turns out by having these quantum-centric workflows and using a new fragmentation technique, it's actually possible to go a fair bit of ways, all the way up to 12,000 atoms, where the idea is that even though this protein, which is 11,000 to 12,000 atoms, and is way larger than you would be able to actually fit onto your quantum computer, you can use a classical workflow to find the right kinds of fragments of those 12,000 atoms in segments that can actually fit on the quantum computer and then stitch some of those results back together. And so here we were able to look at these trypsin and lysozyme types of molecule structures, which are again biologically relevant, and start to get results of the ground state energies that are again competitive with the best classical only methods. Again, so not yet beating, but again showing the capabilities of the scale to even these degrees. Then nuclear fusion, right? Working with Oak Ridge National Laboratory and a number of other collaborators as part of this Genesis mission initiative. We're actually using combinations of AI, HPC, and quantum computing to find better configurations of what are called molten salt blankets. So these molten salt blankets are actually a combination of fluorine, lithium, beryllium that actually line the inner walls of a nuclear fusion reactor. And how they actually bind to tritium is important in order to actually get more tritium for nuclear fusion. And so this is still preliminary work that we've started to explore with them, but in fact here we can use that same fragmentation technique to find optimal mixtures of this kind of molten salt and simulate them and understand how they might interact with, for example, tritium. Then there are, okay, so we talked a lot about these chemistry applications. There are also a lot of exciting application work in optimization as well. So this is actually working with EON and the UKRI, looking at basically energy grid types of optimization networks, right? Where they're performing ways of basically a algorithm called quantum approximate, adiabatic approximate algorithm, and find that they can actually beat a simple classical approach. Now, still not yet, again, quantum advantage, but again, shows the applicability of using quantum computing also for these types of optimization problems. In fact, on the left here, we have published a white paper with a large working group of industries and national laboratories, a optimization benchmarking paper. They identified 10 optimization problems where there are key targets for us to really drive on using quantum computers to try and get an advantage on. We know that they're challenging for classical computers, and they are of the right kind of shape and form that we have the ability to potentially address them in the near to medium term on quantum computers. Similarly here, right, so other workflows with clients, Allstate looking at underwriting optimization. This is a constrained knapsack problem, which they're also applying to basically get a specified risk tolerance, right, solution. And you know, from a classical perspective, they're comparing against some of the well-known methods there as well. From a machine learning perspective, right? So here's where there's the opportunity to look at what are called quantum kernels and feature maps. I think we all know from the perspective of you know, classification that there's a lot of the work that goes into higher dimensional spaces. The question here is, can we use a quantum feature space, right? So when you have a set of qubits, you actually have an exponentially large Hilbert space. Can you use that as a feature space for problems of classification? Tends to be that we've already shown that it can work for very structured types of data, right, with the right kind of shape. But the question is, does that work for kind of data that's in general? So that's really one target of doing quantum enhanced representations. Another one is really using quantum to quantum assisted AI for science, right? So can we actually get features from quantum circuit runs to help us actually train models, right? That then we can still perform prediction out of using those classical models that are trained with quantum data. And then there's a third area, which is to use AI to help us actually discover better quantum applications and quantum workflows, right? So there's a lot of work here in terms of really pushing the boundaries of what can be done in the algorithm space, and AI is a fantastic tool for us to explore this type of work. Just to give you one example of kind of that middle one, right? So this is a deep learning of ground state observables for a particular, what's called a Heisenberg Hamiltonian. We're actually getting samples from this Heisenberg model, which is kind of a spin model on a lattice of our qubits, and we're taking those properties to actually train an AI model that we then use to predict ground state properties out of, right? So it gives you some of the sense for the direction that we can go to really combine these data sets that we can get from a quantum computer to then influence what AI models that we can build around them. Okay, so the last thing I'll just talk about is really, so you start to see these pieces come together, right? And you see these application workflows that are leveraging quantum and leveraging HPC or GPUs. Earlier this year, we published a paper called which showed a reference architecture for what we call quantum-centric supercomputing. It's really designed to be a blueprint, but also one that we want to test and want to work with the community on building out and understanding how it applies and how it can scale. Certainly in many ways, you've seen now that these large problems that you want to solve in chemistry, in optimization and so forth, are going to rely on computing resources of different flavors. And so from a compute layer perspective, we know that we're going to have our quantum computers, which serve as these quantum circuit engines, right? And their job is really to provide quantum circuits of accuracy, right? With accuracy at the scale of, the number of qubits they have and the number of operations that you can perform. But then we know that also we need to be able to process some of those circuits results in near-time loops, so low latency loops that might actually require, again here, GPU clusters or other kinds of accelerators. And those are in a scaled-up type of system, which can be co-located with the quantum computer. And so that's the next box over next to that. And here the key thing is low latency in the order of, say, microseconds to tens of microseconds. Interesting thing here is actually within the quantum computer itself, there's already a lot of classical happening. That's sort of those elements I showed you before, the picture of the classical control electronics, what's actually doing the decoding algorithms and so forth for some of the error correction. That's all kind of inside. But there's this other layer outside, right, that lets us use the results that we're getting from these quantum computers and still also do something dynamic with the results for the circuits that are going back into the quantum computer. And then you have a kind of more batch time or cloud time infrastructure that you also need. Something like that, the Riken workflow, right? But that was really kind of done in batch mode. And in fact, the first instance of that, we were just sharing data, over the cloud, right? Then when we were able to actually co-locate with the co-locate a quantum computer in Japan right next to the Fugaku, we were able to close that loop a little bit and get more interface there and more interplay to be able to go back and forth in terms of how we schedule and resource the workload across those different elements. But that's another key part, right? So there's scale-up systems, there's scale-out systems, right? That can certainly be larger clusters of what need to be built on. And then you need to have interoperability of the networking layer on top, right? Be it Ethernet or some kind of NVLink type of thing. Now, building on top of that, compute layer, you're going to have orchestration and workflow managers. Here, of course, there's a lot that's already done on the classical HPC side, from things that are, of course, done in terms of resource management, right? But we need to make something that allows you to have a hook on to actually run jobs on your quantum side. We've defined a open source interface called Quantum Resource Management Interface, QRMI, that lets you do that. And then above, this is where you start to get your application and application middleware stack. Today, I think people use CUDA, right, for a lot of the GPU work. And there, they breaks it down into various types of libraries that, depending on the applications, domain areas that you're looking at. We see a similar evolution for what you might need on the quantum side. But you need to be able to have those quantum libraries to actually break down those types of application functions into the right kind of quantum programming model that eventually launches the circuit in your quantum computer. And so there's a lot of detail that needs to go into how that application middleware really evolves, but also works in the near term kind of side by side, right, with the classical programming models. And on top really get bottled up into these application library stack that users can start to over time abstract more and more, right? So we really see this over time that the users are going to sit at the top, not necessarily even know what's happening in terms of how the problem gets broken down in terms of using CPU, GPUs, or QPUs, right? But also in this meantime, there's a lot to be done in terms of defining this full software stack. Again, Qiskit, I mentioned before, is our open ecosystem for quantum computing. It's what we see as where a lot of this adoption needs to happen. A lot of this integration with high-performance computing workflows is happening. We built a C++ API, actually, and we also defined a number of interfaces that allows quantum to pair with HPC across Slurm and other resource management interfaces. But here's where we're really excited for a lot of the work to drive towards high-performance computing adoption to really fuel the algorithmic research that sits on top. And then I won't touch too much on this, but we have a whole timeline for our open source projects here for Qiskit that will further evolve really to go deeper into this type of evolution of adopting HPC users, and then over time also developing towards the fault-tolerant solutions that are going to be part of the longer-term workflows. And yeah, so I think it's always fun to end with this view, right? That we're in this advanced computing timeline, right? There are a lot of momentum is happening where we're excited to now bring quantum as kind of this first class citizen together with CPUs and GPUs. And that is really going to help fuel the kind of algorithms and discovery and applications of the future. So thank you.
Thank you, Jerry, for this very futuristic and pragmatic talk, because I predict that in 3 to 5 years, these things, quantum basically is going to be part of our lives. And especially all of us who used to do physics-based, that used to work with Lagrangians, Hamiltonians, we used to optimize with linear methods. Now you can do nonlinear, non-stationary problems that could not be done before, and the world is non-stationary. It's not static data and then learning, etc. You mentioned Feynman, and I always in my slides put a slide from him. He was a giant, he won the Nobel Prize, he was professor at MIT. And he said something that's very true, and you should think about current AI methods. What I cannot model, I do not understand. So I think with quantum and going back to physics and doing things a lot more in a more sophisticated and scientific way, this whole field will progress and solve problems that we cannot do right now. We do have time for several questions. Yes.
Hi, Jerry. Thanks for the fantastic keynote. Historians will probably see the publication of AlexNet as the turning point in AI, when everyone realized that GPU is the way to go. In particular, AlexNet won the ImageNet challenge back in whatever year it was published. What do you foresee the AlexNet moment for quantum computing to be?
Yeah, that's a fun question. To me, I think that's what we're looking for, right? I don't know if I foresee it. I foresee exactly what it is, but a lot of it right now is, at least in the near term, right? A lot of the heuristic discovery that we're looking for by having even the access to the tools and by enabling the combination, right, of quantum with these other computational workflows. Yeah, so to me, my simple guess is something in more the chemistry space to start, but I don't want to rule out any of this. I think the machine learning side and the directions that we can go with quantum and AI are very exciting. I almost put it back on you and the audience here, right? Help define that paper. The resources are here. My job is to make sure that this happens. I see almost this crowd and the rest of the community as the ones that are really help to steer and develop the kind of underlying applicability of this.
Thank you. Hi, thank you for your talk. You were talking about the TAM at 450 to 850 billion. When do you see that coming online? Is it that 2029 or 2033 plus time?
Yeah, that'll be kind of, I would see that's over that course of 2030 to, into the latter part of the 2030s, right? Because you need them at that, a lot of those, you kind of break it down into those proven algorithm advantages, right, that are kind of in that chart, in the kind of quadrant chart that are far out. But also I think the opportunity is there to find where's that value coming from before these proven ones, right? And so that's where a lot of this discovery phase can, I think, have the potential to lead towards economic values that's not even captured by that 450 to 850 billion number yet.
Thank you.
Hey, sorry, yeah, there is a line here as well. Hey, Jerry, thanks so much for the fun talk. I used to be a physics PhD as well and bring back a lot of memories. So whenever we have a new type of compute, right, I can think of the problem in two dimensions. First of all, is enables us. It's a new enabler. Enables us to solve problems that are not solvable before. I think the majority of the talk you talk about that. We can really push the frontier of scientific research. Mm-hmm. This is great. The other dimension I think is for the compute that we do right now, that we have right now, we sort of solve right now, but it might not be energy efficient. Maybe this is a new type of compute that can do it more efficiently. So can you comment a little bit more on the second side of things?
Yeah, it's always that question always comes up, and I think it's an important one to think about. In many ways, the simple answer is additive, right? That it does something mathematically fundamentally different from today's compute. The question is, are there ways of using that mathematical basis to, say, replace what computers are doing today, right? So, can you use it to do something in tensor math better? Maybe, right? So this is where some of that, again, there's both you said it's a discovery phase, but part of the discovery phase, I think, comes down to, how can we disrupt our how we do compute today, right? And so I certainly see the potential, right? You can even see from the power perspective, we're talking megawatts, we're not talking gigawatts. So that energy impact is certainly worth leaning into. But for me, I think the biggest thing is about how do we get more users of the tool to help answer that question.
All right, cool. Thank you.
Is it me?
You.
Okay. So my background was in computer engineering and applied math with a minor in physics when I was an undergrad. As you were talking, one of the biggest thoughts I had was, well, what if we're interested in the hardware side? Where are the opportunities to develop hardware? And you know, I know you pretty much have to cool these things to absolute zero, right? So I just wanted to hear your insights on that, if that was something we're interested in.
Yeah, no, certainly. I mean, so I tried to touch a little bit about it. I didn't spend that much time on it. You know, there's the whole supply chain of things that we need to build at scale, right, and engineered solutions. You know, we're firmly trying to move beyond kind of the physics laboratory environment, right? That these need to be manufacturable, they need to be reproducible. So there's kind of the cryogenic infrastructure element to it. You know, there's vendors out there that are building the cooling engines that let you, you know, make these machines work. We of course need to bring down those prices and costs over time, especially we're talking about large numbers of modules and a large number of systems that we want to build. And then, you know, the other classical work, the other hardware work include, you know, from working on the chips themselves and the design of them to the infrastructure that goes inside the fridge, the wiring, the cabling, the peripheral components that go inside the fridge, the control and runtime engine itself too, right? So there's the whole classical controller that is part of the quantum computer, but inside, right, there's this decoding piece of the error correction, and there's this, you know, you can think of it as there's an engine that feeds pulses, right? And those pulses need to be made, you know, synchronously with low dissipation to control the qubits that are inside the cryogenic environment.
Thank you.
Hi, very inspiring talk. Thank you. Some of the questions that I had were answered like in some form from the previous question. So I'm just wondering about like the QPU data centers. Will they be able to replace the GPU data centers? Yeah. And I'm also thinking around like the energy challenges and the raw material challenges that we face in building these data centers right now. Like, will QPU data centers will be like, do you see it will be resolving, or the same challenge will exist with these supercomputer data centers as well?
So, you know, it's a little similar to that other previous question there, that I believe in the near term it's additive, right? So it's not like we're replacing yet. It's important for us to find how they might tie together. But it's also important for users to figure out, to help work on computational workflows that may lead us to replace how we do workloads today on GPUs. But also I think that, you know, from that scaling sense, it does not scale as dramatically in power, right, or anything like that. And that's part of the interesting draws of this technology.
Yeah, thank you.
Hey, Jerry, very fantastic presentation. My question actually is maybe related a little bit with the first questions they asked you. Currently, like the AI progress, right, has been fundamentally and embedded in how we understand the human brains. AlexNet comes from the, you know, how we understand the visions, which is a little bit similar to the convolutional neural network. Attention is all what you need, which is also related to how human and driving our attentions onto it. Using the quote which you're using from the framing, we cannot model, we don't understand. So quantum, from my understanding, actually is a little bit more conflicted with what we are doing now, right? We don't really understand quantum. I think one thing is which related to fundamental quantum, people use make a joke is if you don't understand quantum, you understand what it is. So my question to you here is, generally we like to borrow insight from human understanding or human brains. If we're trying to bring those type of insight into the quantums, what's your maybe one point about it?
That's a good question. I haven't thought about that way. What we would bring in from our brain perspective. Yeah, it's hard. It's hard for me to say that because my natural inclination for the quantum piece is that that it's most natural to, like you mentioned, neural network is most natural to the brain. The most natural thing for the kind of quantum perspective is really the like physical, like molecular structure, right? It's how electrons are interacting in the real world, right? It's that type of thing that is the most analog, right, to what we have here. And so any kind of like connection here to the brain ends up being a little more abstract, or you have to break it down into that kind of picture. But that's probably an interesting direction to think more about. I don't know. I have a very good answer for you today.
Okay, thank you.
One final question.
Actually, that was the same question.
Okay, thank you.
All right. Thank you, Jerry, again for a fantastic talk. And thank you for attending. And let's give a big hand of applause.
本演讲实录已收录至雷锋网 CVPR 2026深度专区，现已全面上线。专区不仅全面收录了重磅论文的工程化解读、专家前沿演讲，更将持续更新前方记者的第一手会议动态。扫描下方二维码或进入雷锋网 CVPR 专区即可查看。